So the next talk is a shared talk between Draper Labs and Dover Microsystems. Unfortunately, our friend from Dover, Greg, could not make it today, but we have Chris Casinino from, sorry? Thank you. I was trying my best. The principal member of technical staff at Draper Labs.
Can you hear me? Yes, excellent. Thank you. Okay, yes, as mentioned, I'm Chris. Greg unfortunately couldn't make it. It's too bad. Okay, I'm going to try to answer this question, which is, how can we concisely and uniformly express fine-grained security policies? What does that mean? So we just had a session about security, right? And we heard about many different types of security properties: memory safety, control flow integrity in the last talk. And of course, there are many others: compartmentalization, information flow control, permissions, access control. So as a community, we often talk about different types of properties that you might want to have in a system to make it more secure. We don't really have a uniform way to express or reason about those properties. So what I'm going to do is propose a domain-specific language that we've been working with at Draper and at Dover Microsystems for representing security properties, and try to argue that it's general purpose enough to express all those different types of properties that I just mentioned. And this isn't purely an academic exercise. Also, this language that I'm going to describe can be enforced, and we have a simulation infrastructure for enforcing this domain-specific language of security properties on RISC-V programs. And we also have a hardware coprocessor that's a commercial product for enforcing policies written in this language. So I'll talk about those two tools briefly at the end. Okay, so to start with, let me describe this language. So here's an example of a policy written in the language, and I'm going to spend a few minutes on this slide and go through it in detail, so you don't need to understand it all at once. The first thing I want to say is that this language is for describing policies at the architectural level. It describes legal and illegal instructions during the course of an execution of a program. So at the beginning of the policy, we have a section that's called metadata, and the idea of this language is that for each word of memory and each register, the language tracks metadata that describes information about that memory register that might be relevant to the policy you're enforcing. In this case, this policy enforces read, write, execute permissions. Other policies enforce memory safety or permissions, and the metadata might describe different things in those policies. So the metadata in this policy is, you can think of it as being a set of values, and in this policy there are three possible values: read, write, and execute. So if I've got a word of memory, my policy language is going to track metadata associated with that memory. It'll be some subset of these three possibilities. So then we have a section here that describes the policy itself, and the policy is always a sequence of rules, and these rules are checked in order, and each rule can either allow or disallow an instruction or a class of instructions, and every instruction has to be explicitly allowed by one of the rules to be allowed by our policy. So let's take a look at one of the rules in particular. Rules have three parts. This rule in the middle begins with the first part, which is called the op group. And the op group describes a class of instructions to which this rule applies. This rule applies to instructions that store to memory. So op groups are a convenient way to group together instructions for policy purposes that do similar things, right? RISC-V, for example, has several instructions that store to memory. We might want to write a rule in our policy that refers to all those instructions. This also makes the policy somewhat ISA agnostic, although of course you should use RISC-V. Okay, the next part of the rule is the patterns. So these patterns also describe types of classes of instructions to which the rule applies. But this time, rather than being based on the opcode of the instruction, it's based on the metadata that we're tracking related to the memory and registers used by this instruction. So this rule says this rule is going to apply when the metadata associated with the memory word holding the code that is being executed has the execute tag. So that square brackets plus X notation means in the metadata set associated with the memory holding the instruction, there should at least be this execute tag to indicate that this instruction is executable. And then the next part of this line says, describes a piece of metadata we call env, which is the metadata on the program counter register. In this policy, the program counter register's metadata is not used, so we just say we don't care what it is with an underscore. And then last, there's a pattern match on the metadata associated with the memory address that's being stored to. And in this case, we check that metadata has at least the write tag because we're doing a store instruction and we're enforcing read, write, execute permissions, right? And then the last part of the rule, it either explicitly rejects instructions that match the first part, or it allows them and updates metadata. Now, this policy doesn't need to change metadata as it executes, so the last part of the rule doesn't do much. We'll see another policy in a second that does change metadata. So then putting that together, this rule allows store instructions as long as the code has the execute tag and the memory that's being written to has the write tag. And it doesn't make any updates to metadata. The last part of the policy is this section marked require, and this section just describes how memory gets tagged at boot time. So here we see that the stack and the heap should be tagged readable and writable, and that that any code section should be tagged executable. Okay, so that's a detailed walk through one particular policy in our policy language. What I'm going to do now is take a less detailed look at a few other policies to convince you that this language is general purpose enough to express the types of security properties that I discussed at the beginning. And then we'll talk about implementations of this language. So the next policy I want to talk about is for protecting against stack buffer overflows. You all know what a stack buffer overflow is. The stack is an area of temporary storage where program variables are stored alongside sensitive control flow data. And if the programmer is not careful about the way they manipulate those local variables, an attacker can exploit that fact to overwrite the sensitive control flow data, which we typically call the stack frame. This is the return address. So here's a policy that tries to protect the stack frame. The basic idea is this. We're going to use the compiler to, so let me back up. How is the stack frame managed? Well, the compiler inserts code at the beginning of function calls and at the end of function calls that push information onto the stack frame when you call a function and remove that information or pop the stack frame up when you return from a function, right? In particular, the return address. So we're going to instrument our compiler to record where the code is that does this, where the function prologue and epilogues are, and we're going to give the memory holding those special pieces of code a tag that indicates they're special, that they're part of the prologue and the epilogue. When the prologue, when a store happens during a function prologue, we're going to tag the location that gets stored to as special. In this case, we're going to give it the tag frame. And now we know that's part of that special control flow data. That's part of the stack frame. And if another instruction that's not part of the prologue or epilogue tries to touch that frame data, we know we're witnessing a stack overflow attack. So there's a couple of pieces of this I want to pull apart. In the metadata section here, we have three pieces of metadata: frame, prologue, and epilogue. Prologue and epilogue, as I mentioned, are going to be on code, and frame is going to be on memory on the stack. And then I've got a couple example rules here. The first one is the rule that adds the frame metadata to memory during function prologues, right? So it says if the code I'm executing is tagged to be part of the prologue, then allow the instruction and update the tag on the memory that's being written to have this frame tag in its metadata. So that we record the fact this is now special stack frame information. And then the next rule I've shown here is an explicit failure, which we didn't have in the last policy. And this one says, okay, if I'm executing an instruction that's not part of a prologue or an epilogue, and the memory that I'm storing to is tagged as being part of a stack frame, then reject this instruction as part of an illegal stack access, because only the epilogue is allowed to modify stack frames once they've been set up. Okay, so let me do a last example briefly. And this is a very simple coarse-grained control flow integrity policy. So the high-level idea of this policy is this. When I do a jump, I'm going to record the fact that I just jumped to a new location, and I execute a jump instruction. I'm going to do that by adding some metadata to my program counter tag to record that I just did a jump. And then on the next instruction, I'm going to notice that that metadata is present, and I'm going to check that I landed at a place that's legal as the target of a jump. This is very coarse-grained. It doesn't differentiate different kinds of jumps, but it's just an example of the type of thing we can do. So here's a couple example rules from that. The first rule says, if I do a jump, so the op group is for jump instructions, then update the environment metadata, that is the metadata on the PC register, to include the jumping tag. And the next rule says, okay, if I'm executing any instruction, and the environment on the right has the jumping tag, and the code is known to be a legal destination, then allow this and remove the jumping flag, because I'm done jumping. Of course, there's a special case for if I jump to a jump, but I'm not showing that here. Okay, so those are a couple examples of policies in our language. So hopefully, I've convinced you that this is a domain-specific language that allows expressing a wide variety of security policies at the architecture level. Now, that's by itself kind of an academic toy. Is it useful? Is a good question to ask about it. And I think the answer is yes. So we have a couple ways of using this language, not just to express policies, but also to enforce them on programs. And the first is our simulation infrastructure for RISC-V. So we have a simulator that is based on QEMU and has a plugin that does policy checks. So you can write a policy in our language, and then as the program is executing, our QEMU plugin will check at each instruction that the policy is obeyed by that instruction. It tracks the metadata as the program executes, and it checks every instruction whether this instruction should be allowed. And we have many example policies and test programs. FreeRTOS we have running with a cool web server demo. We also have initial support for SEL4. And if you're interested in playing with this, it's online and free open source software with a permissive license. So go ahead and check it out. In addition to the QEMU simulator, we also have a Renode-based simulator there too. It does a similar thing. As an example, here's what you might get as output if you ran a program that had that violated the stack frame policy we looked at before. There's just some output here showing, oh, there was a policy violation, and the code had the store tag, and the memory was tagged as frame, and that's a violation of the policy. So the simulator can track this kind of information. We also have GDB support. I don't have time to go into it, but you can hook GDB into QEMU or Renode and use it to inspect the metadata state as the program is executing. Okay, so last, in addition to software simulation, we do have hardware that enforces policies written in this language. That hardware takes the form of a coprocessor that runs alongside your main, what we call application processor. And the coprocessor tracks metadata during the execution of the program and checks the policies as the program is running and halts the processor or raises an interrupt if a policy violation is detected. We've given talks, Dover and Draper have given talks in the past about this hardware, and I'm not going to go into it in detail, but it does exist. It's available as a commercial product. I want to mention that we do this with RISC-V, right? So right now in our prototypes, both the application processor and the coprocessor, that thing marked PEX on the right there, are RISC-V cores. And we believe, as I mentioned, this policy language is ISA agnostic, so you could change out the application processor, but it's certainly our intent to always use RISC-V as the policy processor, because why not? It's the right choice. So this hardware is available. We collaborate with Dover and Draper on it. And Dover offers a sort of performant commercial version called CoreGuard, and Draper works with government customers to integrate it into defense systems. Okay, so to summarize, domain-specific languages can make it easier to express security policies in concise and informative ways. If you're interested in our particular domain-specific language, you can play with our simulation tools. They're available open source online. We have hardware implementations of this language too, and we'd be happy to talk more about that. Thank you.
Thanks, Trace.